Okay, off we go. Looks like we're recording. Welcome back, everyone. I hope everyone had a good spring break. Real quick, so I just created the attendance quiz. Normally my TA does that. So apparently it's showing up at the top of the list instead of the bottom. Hope everybody found it. If not, you got still probably about a minute and a half to get that in. So make sure to get that in. Time's disappearing. Okay, so back into the math. I'm going to do a very quick reminder of stuff we've been talking about before break. I hope that y'all found a little bit of time, perhaps, to do some keeping up over break. So, but nevertheless, I think it's a good idea for me to do a very, very quick review. So we started off doing scalar line integrals, and we were adding stuff up, quantities that are distributed over a curve, right? And then when we tried to kind of apply those ideas to computing work, what we found is that you end up with kind of a different result. Ultimately, the point here is that the direction you are going matters, right? So this is, in fact, a fundamentally different kind of a problem. If you're adding up mass distributed over a curve, add it up whatever order you want, doesn't make any difference at all. But if you're computing work, it matters because the direction matters, right? Going uphill requires positive work. Going downhill requires, if you will, negative work, or results in you being able to recapture work. Okay, all right, so there's that, and we ended up with this formula and this terminology, and we talked about how to compute. Conveniently, we already had all the tools. We just had to kind of realize that we had all the tools already created, and we did an example where we plug and chug, right? It's really just plug and chug, okay? And then we started to entertain some other questions. So, for example, does the parameterization matter? In fact, in this case, it does. And again, it's about the orientation. Correctly, when you parameterize. Every time parameterize, you are imposing an orientation on the question. And if the orientation has already been prescribed by the question, well, you got to play ball, right? You got to do it the same way that you've been told to do it. Otherwise, again, your answer will be wrong. Okay. All right. Conveniently, when you orient backwards, if you orient the wrong way, right? Very convenient little fact is that, in fact, I'm going to go ahead and zoom in. Oh gosh. That's this thing again. Yeah, okay. When you orient the wrong way, or let's just say, if you orient opposite of the orientation that's given for the curve C, it will just result in a minus sign. This is one of our last results before spring break started. Okay, so now you can view this as documentation of why your bridge is going to fall down, right? That's a perfectly reasonable take. This is exactly how wrong you will be. Or you can view this as an opportunity. Right? This is an opportunity that says, hey, look, if I'm interested in computing a vector line integral, I am apparently perfectly allowed to deliberately orient backwards and then fix it by just sticking in the corresponding minus sign. And that's actually a really valuable tool. So where we did end last time was with this, I'm going to call single example, even though there's actually sort of 4 solutions that I'm going to talk about here. We only did the first 2. We talked about how if you document what your parameter is, think about the orientation as you're documenting your parameter, then you can figure out what the polar angle is and play polar coordinate games, and position is just cosine and sine of the polar angle, and boom, there's your parameterization. Alternatively, this is again super fast review, right? Stuff we did before. Alternatively, you can realize that the parameterization you want, going clockwise, right, is just the reflection of a parameterization that you already know, right? So we already know how to parameterize counterclockwise. That's our very first parameterization, as I recall. Right? And of course that reflection across the y-axis is a pretty easy formula to write down. And then again, boom, answer. And same answer. Okay, so we talked about both of these techniques. And again, if you want to ask the question of, okay, if I'm going clockwise, and I want to know how much work it takes, then you can use the usual formula and plug and chug to compute. So here's the great punchline, though, that we were deprived of because of time reasons right before spring break. We don't have to do either one of these in this case. In this case, we have a much better solution, and it's right here. The much better solution says, if you're, if you're parameterizing backwards, cool. Just, go ahead. Don't forget your minus sign. Right? And that's going to be my next solution here. So keep in mind, we've already computed counterclockwise gives work of pi. That we already did. We've already, turned the crank. We've already, done the effort on that. So, okay, if you want to go clockwise, all right. You want to go clockwise? Well, that's just the opposite orientation of a computation I've already done. Opposite orientations result in minus signs in the result. And, as previously noted, I've already computed how much work it takes to go in the original orientation. That was pi. And so notice that the computation that, before spring break, we just had to parameterize and plug and chug and go through all the computations and inconvenience, and we got minus pi. And check it out. Here we get the exact same value by a much quicker method. Is everybody on board with that? Everybody see the idea here? Right, so we're turning it would be confusing to say turning a negative into a positive. We're turning bad news into good news, right? We're turning understanding of a problem into an alternative solution. It's pretty awesome. Okay. Now, the fourth solution that I'm going to show you to this question is one that I don't approve of. And that is what I'm going to call time travel arguments. All right. So here's the argument. I've seen this on tests a few times, and it's a legitimate problem. Right? You got to keep in mind, I cannot emphasize enough, it's been, an entire spring break since you've heard me say the following, at least, and that is it's not about the answer, right? We're not interested. The answer is secondary importance, right? The importance is the legitimacy of your argument, right? This is a course about reasoning, right? Proper mathematical reasoning. And there's some pretty significant worries that come up if you commit what I call a time travel argument, where, as I have it written down here, for example, t, representing time, starts at a higher value and then proceeds to a lower value. I call that time moving backwards. Well, what does that mean? Right? We've all seen the movies, right? Do we feel like we really understand time travel? Oh, no, come on. No, that's Hollywood nonsense, right? Now, this does result in the minus sign that's necessary for the final answer, and that is true. You will, if you do this, you will, depending on how you do the algebra, and as long as you don't make any other misinterpretations, it would get you to the right answer. But it's very fraught reasoning. Because for one thing, again, you're invoking time travel, right? I'm not clear that you understand how that works, to be silly. The other thing is, you gotta realize, formulas that we've written down previously, and that are part of our machinery for how we compute these things, are no longer true, right? This goes away if you write down time moving backwards. The velocity is not the derivative of the parameterization anymore. right? So the framework that we have set up that allows us to compute vector line integrals involving a whole bunch of relationships, including these. Yeah, you can't use that framework because it doesn't work anymore. And yeah, it happened in a happy coincidence probably to get the right answer, but again, not what we're interested in, right? So this is very, very fraught, and may I point out, completely unnecessary, right? There is no advantage to doing this. Because anytime you would have wanted to do this, you can just do this instead, right? So don't make bad arguments unnecessarily. All you got to do is just tip the cap to orientation for your minus sign, and then stick within the established framework. All of our formulas work out great. You got options there. Does that make sense to everybody? Everybody see why I don't like the time travel arguments? Right? And again, you don't lose anything here, right? I want to make sure your arguments stay tight. Okay. Alrighty. Okay, moving along. So, we've seen this construction, vector line integral, to compute work. That's the only application we've seen so far. If you want to compute the amount of work it takes to move through a force field, then boom, that's how you do it, and we've justified that and everything. However, do keep in mind, this assumes that the vector field in question represents forces. So that's not always the case, right? Not every vector field we write down represents forces. Some of them do, right? Electric fields, gravitational fields, yeah, sure. But sometimes, right? Sometimes the vector field represents a fluid flow, not a force. No force is involved. And if that's the case, we've got a totally different physical scenario. We can't assume we're going to get the same physical result, and we don't. So the question is, what is it then? Right? What is a vector line integral if the vector field in the integrand represents the velocity of a fluid as opposed to a force? And this is we're going to have to do a little bit of a clever argument here in order to be able to get an answer to this question. So bear with me. Roughly speaking, I'm going to ask a question that doesn't seem to be relevant. The answer will not be the vector line integral we're interested in, but this not quite relevant question and the not quite relevant answer, after I get that done, I'll be able to kind of tweak the whole thing in a way that will actually give us really exactly what we want. So this is, for the moment anyway, a bear with me kind of a situation. So here's the question we're going to ask. I've got a oriented curve, right? Like so. And now this is going to seem weird, but I'm going to think about a thin region kind of surrounding that curve. Specifically created by taking a cross-sectional area, A, and kind of dragging it, if you will, sort of along the curve. Right? So now it's a weird region, granted. But, okay, so we've got this region. There's a fluid flowing around, apparently, because that's what our vector field represents, the flow of a fluid. So there's a certain amount of fluid in that region. And here's what I want to ask. The big question, looking at all of the fluid, every little piece of fluid in that little kind of tube, if you will, every little piece of fluid, to some extent, is going to be flowing along the curve. Right? Despite the fact that, of course, to some other extent, it's going to be flowing perpendicular to the curve, right? I mean, the flow doesn't have to be exactly along the curve because, well, it's just a random curve and you've got a completely disconnected fluid that's flowing around. So the fluid will to some extent be flowing along the curve and to some extent flowing perpendicular to the curve. I want to know altogether, looking at all the fluid, what is the combined extent to which the fluid is flowing along the curve? I know it's a weird question. Right? Anyway, let's play along. No big deal here. In fact, I can talk about. Let's see here. I just don't want to mix up my colors. Here's a piece of fluid, and it's not hard to write down how much fluid that is. It's just area times thickness. That's how much fluid is in that little piece of our sort of tube-like domain of fluid. And if I want to know the extent to which that is flowing along the curve, well, no problem. The vector field, right? The vector field represents the actual flow of the fluid. What I'm interested in is the component of that in the direction of the curve, and components are computed with dot products with unit vectors, and don't forget capital T is our unit vector in the direction of the curve. So, no big deal. For each little piece of fluid, I'm interested in how much fluid is it, and to what extent is it flowing along the curve. You write that down. Okay. And then having written that down, I can kind of answer the question, which is, let's see here. So we were looking for the grand total amount that the fluid is flowing along the curve. We've broken that up now into little pieces. And apparently that is all of this business. Notice that the A, of course, is a constant. We're dragging a constant area around this curve, and so we can factor out the A. And then we notice, get all this to cooperate, we notice that this part of our answer, not the actual complete total answer, but that part of our answer is exactly a vector line integral. So we asked a question that we ultimately don't care about. We have an answer that's not actually what we're interested in. But the answer includes what we're interested in. And this is what's going to allow us to actually answer our, to get what we truly want. So one way to think about this is that the vector line integral can be interpreted then as what you get when you divide this area over here like that. Right? And that integral then is quantity per unit area. The vector line integral says per unit area, obviously, and by the way, let's just take a quick moment to recognize this area that I'm using to define my tube. More area means a bigger tube means more fluid. Right? So bigger area, bigger answer. Of course it is. So you would expect area to be a factor there. So it's pretty natural if you know area is going to be a factor. It's pretty natural to say, look, let's just keep it simple and talk about how much of this fluid flow per unit area, because if area is just a multiplicative factor, it's ultimately irrelevant. So quantity per unit area is a pretty natural thing to want to talk about, and conveniently, that natural thing to want to talk about is the vector line integral, and that's our interpretation of vector line integrals in this context. How we doing? I know it's a lot of details in that computation, and it's also kind of a weird thing to want to talk about, but it's a fairly crisp answer. To some extent, when you are looking at a flow of a fluid and there's a curve involved, to some extent, the fluid is flowing along the curve. To some extent, it's not flowing along the curve. This just says, altogether, to what extent is the fluid flowing along the curve? And it's a really, really valuable interpretation. So make sure that you digest this result. I think the argument justifying it is satisfying myself, but you definitely need to make sure that you digest this interpretation of vector line integrals, again with the understanding that our vector field, in this case, our vector field represents the flow of a fluid. Okay, no forces. So I'm going to give you some kind of examples, hopefully geometrically satisfying examples, in a particular context. So there's a particular special case of this construction, which is when your curve is a closed curve. It turns out that this is really, really important. It comes up a lot in engineering, by the way. It comes up tremendously in engineering. With fluids, right? This interpretation with fluids, really big deal in multiple ways. So anyway, the big idea there is if we've got a closed curve, for example, let's look at this closed curve here. Let's say it starts there and it goes around in the direction that's indicated and it ends right back where it started